Dobry den, good day. I'm Pavel Kroupa, and today I will lecture on the meaning of the cosmic microwave background radiation field for cosmological models and the role elliptical galaxies have in this problem. This is a lecture I was invited by Jaroslav Haas to hold at the Astronomical Institute at Charles University in Prague on December 10th. He was eager to learn more about the recent thinking and work I was involved with in collaboration with Eda Gheorghiu, who is at Nanjing University in China, and Nikolaos Samaras, who defended his doctoral degree at Charles University a few months ago. After the lecture, a few students approached me suggesting this lecture be made available more widely, which is why I'm recording it therewith. Imagine we have trajectory data of a falling apple. That means we record the position of the apple as a function of time. You will agree that the trajectory data of a falling apple must be reproduced by every theory of gravitation, for example, the Newtonian, Einsteinian, or Milgromian formulations. Now imagine the Planck CMB data. You will all agree that the Planck CMB data must be reproduced by every theory of cosmology. For example, the lambda cold dark matter model or the lambda warm dark matter models, cosmologies without dark matter even. For example, based on the Milgromian formulation of gravitation. Some of us might even be convinced that only the standard lambda CDM model can account for the Planck CMB data. Is this true, though? Let's first introduce the standard model of cosmology, also just called the SMOC. It is based on two fundamental assumptions or axioms. First of all, that the Einsteinian-Newtonian formulation of gravity is valid everywhere. All matter is created in the hot Big Bang. Is the second axiom. These are very sensible assumptions, by the way. They make physical sense, and with this we have a mathematically formulated model which we can compare with observations. These observational data would be, for example, the cosmic microwave background radiation field, galaxy rotation curves. So when we calculate how a universe evolves with these two assumptions, we will see that this model is immediately falsified because structures simply don't form in it, because there's too small amount of mass within the universe. So as the universe expands, the matter is diluted before it can actually make structures. In order to uphold this model, nevertheless, scientists have introduced three auxiliary assumptions. Since the universe appears today completely flat, one invokes a hypothetical inflation field which expands the universe extremely rapidly by an extremely large amount, making it appear flat for an observer and within the horizon of an observer. In order to enforce structure formation, one adds about 5 times as much matter into the model. This type of matter, which we call dark matter, has to be exotic in the sense that it's not part of the standard model of particle physics. So it doesn't interact electromagnetically and also not with a strong or weak force. So it's only gravitationally active. It can be interacting with a weak force, actually, but overall it's an inert type of matter which is not described by the standard model of particle physics. With this, one can actually find, if one does now a calculation with these two fundamental assumptions and these two additional hypotheses, that a universe full of galaxies does evolve with galaxy clusters, filaments, because now there's enough matter which can enforce the structure formation through the gravitational forces which develop as overdensities evolve. However, it's found that this universe with this amount of matter would be decelerating because of the self-gravity. So it's expanding, but the expansion would be getting less with time. And what we observe, however, is that the universe appears to be expanding quite rapidly, even today, more rapidly than it should be if we had all that matter in it. And so one has to postulate that there is a additional field, which is referred to as dark energy, which is now starting to be active and is starting to pull the universe apart again, causing a new epoch of accelerated expansion. And so these are the three pillars of cosmology, and the dark matter particles, one should note, can be cold, warm, fuzzy, or axion. Cold meaning that they can be fairly massive, even little black holes, for example. There could also be massive black holes. Warm, so there would be less massive particles. And they could be fuzzy, which means they have the Broglie wavelength, which is significant. And there could be axions. Now, axions are actually an interesting candidate because they are motivated from the standard model of particle physics through problems one has in terms of CPT violation. Now, it's important, so it looks like this cold dark matter could be anything, and it basically, we don't know what it would be because we can only detect its action through its gravitational action. So we can only detect it through its gravitational action. However, actually, the particles are fairly well constrained in terms of their masses. So, for example, massive black holes are excluded because dwarf-spheroidal satellite galaxies have to contain about 100 times as much mass than in their stars in dark matter. So if there were like a million solar mass black holes, then there would be a dozen or maybe 100 black holes which would then kick each other out of the system, such that today the dwarf-spheroidal satellite galaxies would look quite void of dark matter. And so this is an example how we know that the mass of the dark matter particles must be much less than even stellar mass black holes. There's quite a lot of literature on that. At the same time, we have to explain again the dwarf-spheroidal satellite galaxies with their amount of dark matter. And so the de Broglie wavelength in this fuzzy dark matter particle approach has to be such that it does not interfere with these satellite galaxies, which have an expanse of only a few hundred parsecs, that these satellites appear to be dominated by dark matter particles. And so at the end of the day, when one puts all these constraints together, it turns out that for all practical purposes, the dark matter, whether it's now axions, fuzzy, warm, or cold, it has to basically behave like cold, warm, dark matter in order to explain, at least hopefully, galactic rotation curves, which go out to some dozens of kiloparsecs, as well as the observed structures and mass content of these dwarf-spheroidal satellite galaxies, which are satellite galaxies orbiting our Milky Way. And so we have stringent constraints on this dark matter density, and the dark matter must be particles, otherwise we have a not lambda cold or warm dark matter model. Now, this is important because some colleagues tell me, well, we can't actually constrain the existence of dark matter apart from finding it in the laboratory or through some experiment, because it could be anything. And I disagree with that, because if we are contemplating the idea that this dark matter is some sort of fluid, then we are looking at an entirely different model. It's not the standard model of cosmology anymore, because then structure formation, so this and the confrontation with observations would be something completely different. So we would then have to investigate such models and see how galaxies evolve in these, if they even can form. So that's something which has not been studied, and that is not the standard model of cosmology. The standard model of cosmology, the currently favored one, the one which everybody on the planet is basically convinced is the correct description, I should say nearly everybody, assumes dark matter to be particles, and the density of these particles is well constrained, because this formulation of the cosmological model, which is referred to as the standard model of cosmology, must fulfill these observational constraints. And so dark matter is the core pillar of the model. If dark matter does not exist, remember, it is still only a hypothesis, it has not been discovered, then the entire framework collapses, because without dark matter, structures cannot form. So if we start with this initial condition of the small fluctuations and try to find if galaxies form without dark matter, then it does not work. No structures will form, because there would be too little mass in normal matter to become self-gravitating in regions to collapse and make galaxies. So actually, we have been testing for the existence of dark matter particles using Chandrasekhar dynamical friction tests on various systems like galactic bars and the orbit of the small imaginary cloud around the large imaginary cloud. And it turns out that all the tests which have been done rule out the existence of dark matter with much more than 5 sigma confidence. It's a very, very hard, very extremely confident deduction. Dark matter particles do not exist. They have also not been observed or discovered and detected. And of course, if something doesn't exist, you can't find it, obviously, right? And the particularly stringent point here is that the small imaginary cloud has been orbiting the large imaginary cloud for at least the past 3 or so billion years, and with about 4 orbits, without an indication of orbital shrinkage. And we know this from the correlated star formation histories of both galaxies, which have now been mapped out very well. And so if both galaxies had these dark matter halos around them, then they would merge within 1 billion years on this type of orbit. And they haven't. So this completely and extremely confidently rules out the existence of dark matter. So this whole model is actually already ruled out. It's not a viable description for the universe. But let's look now at the key observation evidence for the hot Big Bang model, which is given by the cosmic microwave background observation. So what is the cosmic microwave background? It was hinted at by early data already in the 1940s, but the formal discovery is attributed to Penzias and Wilson in 1964. The widely accepted interpretation is that the CMB consists of photons emitted when the post-Big Bang plasma cooled sufficiently down to about 3000 Kelvin for hydrogen to recombine, allowing the photons to free stream. So this is basically what happens at the surface of a star. We see stars like the sun to have a surface, and that's simply that region in the plasma where photons can propagate freely outwards without scattering on electrons or protons. And so that's why they appear to have a surface which is called the photosphere. So the CMB is essentially the photosphere of the hot Big Bang. It's a surface of last scattering or just relic radiation. It was released at a redshift of about 1100 when the temperature was about 3000 Kelvin. And today it is understood to be a near perfect black body with a temperature of 2.725 Kelvin with an incredible small amount of fluctuation. If you look at one direction and then you look at another direction of the sky, the temperature is basically identical to within 10 to the minus 5. So the temperatures deviate from each other at the level of 1/100,000th So it's a very, very smooth cosmic microwave background field of photons. The maximum emission of this black body is at 1.9 millimeters, wavelength of 1.9 millimeters. And this we need to remember as an important number, and this one too. These are two important numbers characterizing the present day quantification of the CMB photon flux. So these fluctuations pose the initial conditions for studies of cosmological structure formation. Which initial conditions to use in cosmological simulations? So currently it is thought that the fluctuations in temperature of the CMB are the initial conditions at this redshift that any cosmological model must fulfill. Okay, so we take the fluctuation spectrum, a model, for example, the lambda CDM model, evolve to a certain redshift, say 100, to be safe for 200, where from here to that redshift, the growth of the structures is in a linear regime. Beyond this redshift of about 100 to 200, 100 in lambda CDM, 200 in mode-based models, the structures begin to collapse through self-gravity, and the evolution goes into the nonlinear regime, and for that we need supercomputers. So one then takes this fluctuation spectrum transformed to this redshift of, say, 200 in mode-based cosmologies, and these fluctuations are fed into a supercomputer, and with a particular computer code. For example, we use the Phantom of Ramses code, or if we are working with lambda CDM or lambda warm dark matter models, we would, for example, use the gadget code. And these codes then solve the equations of motions of the particles, which we put into the computer at this point, at this redshift, to see these fluctuations. So a little bit over density here, a little bit under density over there, as coming from this initial fluctuation spectrum, to then study how these density fluctuations evolve through gravitational, through gravitation to the galaxies, galaxy clusters, filaments we see today, and then we can compare the output of such simulations with the real universe. So can only the lambda CDM model account for the Planck CMB data? So the CMB power spectrum can actually be reproduced by non-lambda CDM models, contrary to popular thinking. So here's an example of what we call the new HDM model, which is a mode-based cosmological model, and it assumes the same fluctuation spectrum as the lambda CDM model at redshift of 1100. So it assumes the previous evolution of the universe up to this redshift 1100 was identical. So there's a photosphere which releases the photons at this redshift, and at that redshift one had this power spectrum, which we can see here as the blue points. That's the Planck observations, which are extremely well matched by the lambda CDM model, the SMOC. However, we can see that the optimized new HDM model, which comes from the work of Nick Samaras in Prague, fits these data nearly equally as well. So the green curve, which is this optimized mode-based cosmological model without cold dark matter, is an excellent reproduction or fit to these Planck data. The red one is the new HDM model published by Angus et al., which was based on Corby data, Corby and WMAP data, I think, which shows a slightly worse fit. Nevertheless, good enough actually to demonstrate that these type of cosmological models do work. So this model is a model in which galaxies form, galaxy clusters form, without the help of cold or warm dark matter. It does contain a sterile neutrino component, which is a hot dark matter component, but the sterile neutrinos find a better motivation in particle physics, and so it's a less exotic model. Furthermore, these models, as we can see, are in a good reproduction of the Planck observations. they also automatically solve all the problems we have with galaxies. So they are definitely preferred cosmological models compared to the smog, which in any case is ruled out because dark matter has been falsified to exist. So dark matter doesn't exist. It has never been discovered. It will never be discovered. And these models are out anyway. So we have to look at models which are essentially similar to these models because of the equations of motion. They have to be effectively Milgromian, since the observed galaxies are basically Milgromian objects. So the CMB power spectrum is also reproduced by an entirely different type of model. So again, working in Prague, Skådis and Složnik have published a full relativistic formulation of a gravitational theory, which includes Mond, Newton, as well as Einstein's GR in the appropriate limits. And you can see that this relativistic formulation of gravitation fits the Planck CMB data exceedingly well. This model, this relativistic model by Skådis and Složnik, however, does require the addition of a scalar, a vector and a tensor field, which are three new fields, which the role of which now have to be discussed. So what is the physical meaning of these fields? And so there's very interesting and exciting research to be done in this direction, and also to study the dynamical influence of these fields on structure formation. But it's fundamentally Mond in the galactic scale regime, and so automatically these models also solve all these problems which we have with galaxies, for example, the co-cusp problem, the flat rotation curve problem, and missing satellite problem, in the sense that there are far too few satellites which we observe compared to the original predictions from the lambda CDM model, which is anyway ruled out. So the lesson one here is that this proves that the lambda CDM model is not unique in reproducing the Planck CMB data. Other distinctly non-dark matter-based hot Big Bang models equally fit the CMB data. For example, the Mond-based cosmologies additionally automatically solve nearly all known lambda CDM problems in galaxies. These are thus definitely preferred over the lambda cold or warm dark matter models. And I always want to re-emphasize that these models have anyway been falsified, ruled out, because dark matter does not exist. The Chandrasekhar dynamical friction test completely rules out the existence of dark matter particles, and they have not been found, and they will also not be found because they don't exist. So we are forced to actually go into these type of models here. So this is a nice example of the fact that empirical data can never prove a theory. So we have data, and there are multiple theories which can account for the data. So we have to use additionally independent data to weed out those theories which are inconsistent with some set of data. And so in this particular case, we have the nice example that the Mond-based cosmologies, as well as the dark matter-based Newtonian models, the standard models, fit this particular set of data, which are given by the cosmic microwave background. But then the dynamical friction, which comes from the dark matter particles, if they were to exist, rules out these models. So they are off the table, and we are forced to study models which are Mond-based cosmologies. But are Planck CMB data truly valid for all hot Big Bang models? So here's an issue which I don't think one will hear being explored elsewhere, and it is as follows. So imagine we have indeed a photosphere of the hot Big Bang released, where the photons are released at the redshift of 1100, and we don't know what these fluctuations are at this point. We just know that there was this event, and the photons are released, and then as these photons propagate through the growing structures, as the universe evolves, galaxy clusters begin to form, galaxies begin to form, voids emerge. And along the way, these photons suffer multiple effects. So first of all, deflections through the weak lensing. So as the photon propagates and the universe expands and structures evolve, gravitational potential wells develop and they deflect the photons. And this depends on when these gravitational wells develop. So if they develop late, the deflections will be different statistically than if they start evolving very early in the universe. Then the energy changes, the energy of these CMB photons released at this time change through scattering on electrons. So these potential wells accumulate normal matter, and some of it is ionized. So there are free electrons, and the photons scatter on these free electrons, changing their energy. And this again depends on when the structures evolve in the model. And then the energy of the photons, of the CMB photons, change through evolving potential wells. So a photon entering a galaxy cluster will, when it leaves this potential, when it passes through and then it leaves this potential, the potential is changed a little bit because of the evolution, of the expansion of the universe. And so the photon has changed its energy as a consequence. Furthermore, as the universe evolves, new photons appear from foreground, which means stars begin to shine, they are born and begin to shine, galaxies form and become more massive as time progresses. And so with all these effects, we observe today at redshift of 0, a background which has fluctuations, and these fluctuations are given by all these effects. And so we have to statistically remove how these effects affect the photons as they propagate through the universe. So we have to subtract these for these effects to then obtain an estimate of the true fluctuations at the redshift of 1100. And this means that these, what we then infer at this redshift for the power spectrum of these fluctuations critically depends on these corrections. But these corrections cannot be observed. We can only infer them from a model because we don't know whether galaxy clusters begin to form early or late, but the lambda CDM model, for example, tells us through the supercomputer simulations when galaxy clusters started to have an effect on the weak lensing, for example, and scattering on electrons and so on. So the point here is that what we know about the CMB today has been calculated from the observed background, the raw data, after these corrections have been applied, which are, however, model specific, i.e. in this case, lambda CDM specific, which means that the CMB power spectrum, which is published today and which everybody uses, including the Mond community uses as the initial condition here, is strictly only valid for a lambda CDM universe. And we don't know what it is for a Mond-based universe because this calculation has not been done. We haven't taken the raw data, quantified how structures evolve in a Mond-based cosmological models, and there are many different possibilities for Mond-based cosmological models. And so we don't actually know what the power spectrum looks like for Mond-based cosmological models, as an example. And so the initial conditions at redshift near 1100 must be recalculated for every cosmological model separately. Given the CMB observed at redshift 0, i.e. the raw data, every cosmological model has its own unique CMB power spectrum at a redshift when recombination occurs in that model, which of course, again, it's not clear. Is that for every cosmological model really truly at 1100? From raw Planck data, we need to apply an iterative procedure to uncover the temperature fluctuations at recombination in every particular model. So the thing is, the point is that we take the raw CMB, do a correction, get a power spectrum, apply the model to see whether the structure formation actually gives the raw data, and there will be deviations. Then we have to adjust the parameters in the model, for example, the amount of matter it contains or how rapidly it's expanding, to then redo the corrections from the raw data to a new version of the initial fluctuations at the redshift of corresponding to recombination, and then redo the whole process multiple times, and hopefully the process would then converge to a unique solution for the power spectrum at recombination in a particular model. And this type of work has never been done. And so here's lesson 2. The currently known CMB and its power spectra are only valid for the dark matter-based hot Big Bang models. However, dark matter-based hot Big Bang models have been falsified because dark matter does not exist. It is wrong, logically inconsistent, physically false to force a non-dark matter-based cosmological model into the currently published Planck CMB data, which means that the Mond community, which has been trying to develop Mond cosmological models, has erred here. They've done incorrect work. But is the CMB truly the service of last scattering, the photosphere of a hot Big Bang? And this is based on the work we did with Eda Giorgo and published in 2025. So I'm now stepping back, and not only am I arguing that each cosmological model requires its own power spectrum at a redshift of recombination, but I'm now actually starting to ask the blasphemous question, what is the true physical origin of the CMB, given that we are now entertaining non-standard model of cosmology, so non-dark matter-based models, and given this issue of what is the initial fluctuation spectrum, we have to also now open our minds to the possibility that we might be looking at a form of radiation in the cosmic microwave background, which may not wholly come from a recombination event. I mean, does every model have a recombination event, for example, is basically the question here. So this was discovered, by the way, it was not the aim to look at this, but it's a serendipitous discovery of research I was involved with Eda Giorgo, and what I'm now going to explain to you comes out of that. It was not the aim of this research, it's a side outcome which I'm now explaining. So there's a hitherto unknown foreground, and let me explain that. That's these forming elliptical galaxies and their role in what we observe as the cosmic microwave background. Now, to start the story of discovery, we have to realize that elliptical galaxies are metal-rich. They are in fact supersolar, and they have a high alpha over iron ratio. I will explain in a moment the implications of this. So here is data from this publication by Lee et al. Of the metallicity versus the mass of these galaxies. So blue dots are disk galaxies like our Milky Way, and the red dots are early type galaxies, basically elliptical galaxies. These are the massive galaxies at this end, at this mass, and they are the lower mass galaxies. Our Milky Way has a mass corresponding to a velocity dispersion of some 150, 250 or so kilometers per second, and so our Milky Way would be about in this regime as a blue dot. It has about solar metallicity, and so it's a fairly typical galaxy of that mass. You can see there are many blue points in this regime. And the elliptical galaxies we can see extend to the very massive end. So these very massive galaxies are mostly ellipticals, and they are supersolar, so typically above solar. If you draw a line here, you can see that they're all supersolar up here. They have more metals in there relative to hydrogen than the disk galaxies. And here we have some work from Daniel Thomas and collaborators from 2010. They looked at a few thousand galaxies, and there are these diagrams as well as others in their research paper. First of all, they looked at a few thousand early type galaxies. So this gray cloud are all early type galaxies. However, in their sample, they find that there's this smaller set of early type galaxies which have evidence for rejuvenation. So they started forming stars again at some particular epoch, and they are the rejuvenated galaxies with colors which show that they have a young stellar population in them. And the bulk of their population of galaxies they studied are, however, dead and red galaxies. So they are ancient galaxies with no evidence for star formation in the past billions of years. And you can see that these extend up to ages as old as the universe up here. And so this line tells us that the more massive, so the x-axis is the mass of the galaxy, the more massive ellipticals are typically also older than the somewhat less massive ellipticals. Interesting is that these rejuvenated galaxies are ellipticals in isolation, more isolated, while these are in denser environments, which means that the ellipticals in isolation were able to acquire gas and reform stars, it seems. And these results are incredibly interesting. And so these galaxies are, again, super metal rich. So we have here the solar metallicity. This is the mass of the galaxies. We can see that they're all metal rich, but the most massive elliptical galaxies here are supersolar. So the Milky Way has a metallicity near zero here, and you see that these are all very metal rich. So they have per hydrogen atom much more metals being any element higher than helium. And so they are enriched in metals compared to the Milky Way. And a really important result is also that these elliptical galaxies are alpha enhanced. So the ratio between alpha elements versus iron elements is supersolar. So the solar values here. And these galaxies have far more alpha elements in them, in their stars, per iron than the Milky Way, which is at about the bulk of the Milky Way, so the thin disk of the Milky Way population, which is in this regime here. So the Milky Way, in fact, has a mass around this range, so this is where the Milky Way would be. And so this alpha enhancement is a crucial indicator of how quickly these galaxies formed. So do the observed real elliptical galaxies contain stellar populations with a cosmological spread of ages? And this question is central in understanding how elliptical galaxies form. Because if elliptical galaxies form from the mergers of many disk galaxies, as is commonly believed by nearly everybody, then the emergent elliptical galaxies would have stars in them which span the entire range of ages of the whole universe, because disk galaxies continue forming stars until they are forced to stop forming stars. And since this merging would continue up until today, we would expect a very large range of ages of stars in these elliptical galaxies. So chemical enrichment modeling is the essential tool how to understand or answer this question. First of all, when star formation begins, in the gas, from the gas stars form, and when the massive stars after a lifetime of about 50 million years explode, they enrich the gas from which new stars form with elements like oxygen, magnesium, and iron, basically all the elements. And so the ratio between oxygen, magnesium, and iron, and these are alpha elements, remains about constant as long as core collapse supernova enrich the gas. And so if we see a galaxy with a stellar population in it, which has a ratio between these elements and iron, which is high, then we know that those stars formed before supernova 1A started to explode. So supernova 1A come from intermediate mass stars. They are white dwarfs, which are either accreting from a companion star or two white dwarfs which merge, and then they explode as supernova 1A, destroying the entire star, such that all the elements synthesized during this explosion and also previous to the explosion in the precursor star are released. And so the supernova 1A explosions release a lot of iron into the galaxy, which means that we now have the gas which was enriched by the stars which become core-collapse supernovae, and the ratio between alpha elements and iron is about constant as long as this enrichment continues. But then when supernova 1A begin to explode, they contribute mostly iron, and so this ratio alpha over iron decreases because now supernova 1A are dumping iron into the gas from which new stars form, and so the newly formed stars then have smaller values of this ratio than the stars which formed from gas enriched only by precursors of the core collapse supernovae. And so if we now see two galaxies, and the one galaxy has a ratio alpha over iron, which is for its metallicity, which is high, and another galaxy, say at the same metallicity, but which has a small ratio alpha over iron, then we know that the first one formed the stars very quickly before supernova 1A started to explode. So when they start to explode in the first galaxy, which has a high value here, star formation was done, was finished. And then the supernova 1A explode, but they release the elements, but it doesn't go into the gas which forms stars anymore. If we see a galaxy with a small value of this ratio, but the same metallicity as the previous galaxy, then we know that this population of stars formed over many billions of years, because most of the stars would have formed from gas which was enriched by supernova 1A, and they start to explode after about a few 100 million years to a billion years. And so this ratio tells us, is a clock. It tells us how quickly a stellar population built up. If it's high, the stellar population formed rapidly before supernova 1A started to explode. If it's low, the stellar population built up over many billions of years with gas enriched by supernova 1A explosions. So the answer to this question is no. Real elliptical galaxies do not contain stellar population with a cosmological spread of ages. And the reason for this no is as follows. Observations show that more massive elliptical galaxy is, the earlier and quicker it formed. And this is the downsizing problem, which was already discussed by Cowie et al. 1996, by measuring the fraction of galaxies that have active star formation as a function of redshift and galaxy mass. Massive galaxies shut down more quickly. How can we verify this? And there are multiple ways to verify this initial result, which of course is a disaster for lambda CDM cosmology. I'll show in a moment. One can use abundances of alpha elements, as I've just described. And this was the seminal work of Daniel Thomas et al. They showed that these results indicate that the more massive the galaxy, the shorter is its star formation timescale, and the higher is the redshift of the bulk star formation. So the population was simply older, the more massive the galaxy is. And this finding is not compatible with the prediction from models of high-redshift galaxy formation. Independent of these data, and you can see this is now independent of their work, but leading to the same result. And independent of this analysis, McDermott et al. Did a stellar population thesis of elliptical galaxies. And so they basically fitted stellar spectra until the stellar spectra, this model of a galaxy in terms of its spectral energy distribution, fitted the observed spectral energy distribution of a galaxy, finding that they were only allowed to add very, very old stars in order to explain the observed spectra. And also that the dispersion of the ages of the stars was very small, and in fact smaller for the more massive galaxies. And then Jikang Yan and Teresa Rabkova, so Jikang Yan did his PhD in Prague, and Teresa studied also in Prague, performed full-scale chemical enrichment modeling, so including alpha elements, but also all the other elements, again finding the same result. So elliptical galaxies are, so we could see we have here 4 independent studies, and they independently of each other find exactly the same result, and that is that massive elliptical galaxies formed very, very rapidly and very early. So these downsizing results suggest that elliptical galaxies form on a free-fall timescale. In fact, we now know how quickly a galaxy formed given its mass. And so we find here that the massive galaxies, this is the mass of the galaxy, like here, this nearly 10 to 11 solar masses, formed on a time scale comparable to 1 billion years, and the somewhat less massive elliptical galaxies formed on a somewhat longer time scale. And this time difference between the massive ones and the less massive ones, one gets automatically if we have a protogalactic gas cloud which is just allowed to collapse, and from the same radius, then it will collapse faster if it's more massive and less fast than if it's less massive. And the numbers come out exactly right for a simple collapse model of the formation of elliptical galaxy. And this is shown here in this work by Wittenburg et al. And Robin Erpen, who also worked in Prague. So we have here a protogalactic gas cloud, and we allow it to now collapse in the computer, and you can see that it collapses, forms stars, and it spins up and forms a rapidly rotating, fairly compact spheroidal galaxy, an early type galaxy. It uses up its gas, and you can see the bubbles are supernova explosions. So it pushes out part of the gas, which heats up and becomes an outflow of hot gas. And the inner part of the galaxy uses up the gas, so the star formation subsides. And here's now the same, but stars only. So we now look at how the stars emerge. So you can see now the galaxy is there. And the important thing here is that the collapse, as you can see, nothing happens. And now the collapse begins at the center. The center, that's where the starburst begins. So that's where the oldest stars form. Where the stars form first, and then as the time progresses and the collapse proceeds, the star formation climbs outwards, and so we expect a radial gradient of ages from the inner part to the outer part, where the inner part is the oldest in these simulations. And what is found, that's exactly what is observed. So this is a recent publication by Yegathe-san et al., where they looked at 3 elliptical galaxies, and with the modern instruments they were able to take spectra in each pixel and study the stellar population along the line of sight in these pixels, and and do population synthesis studies along each pixel. And so they find, for example, here in this galaxy, that the center part is indeed oldest. In fact, these numbers, so these are just the fits to the stellar population modeling, are nominally older than the age of the universe. And as we go outwards, the stars become a little bit younger. The same in this galaxy, see here, and the same in this galaxy is overall very old. Then here we have the light-weighted ages, which show basically the same result and indicate even older ages, in fact. And then we have the mass-weighted metallicity. So we see that the inner parts of the galaxies are supersolar. You can see this ratio here is relative to the Milky Way is supersolar, just like the previous data, and the outer parts are very comparable to the Milky Way. So overall, the bulk populations of these galaxies are very metal-rich, supersolar, and compared to the Milky Way. So this beautifully confirms the previous results in this most recent, very detailed and very, very nice study by Yegathe-san et al. So from that one can construct these growth curves. So we have here the mass of the early type galaxy versus the look back time, which means that the hot Big Bang is nominally here at 13.8 billion years. And The observational data from Yegathe-San et al. Indicate that these two galaxies that began to form before the hot Big Bang, normally as a formal solution, and very quickly achieved their mass we see today. And this other galaxy started to form significantly before the hot Big Bang. And these gray curves here are models of these collapse simulations, which essentially tell us that there's excellent agreement. So this very much informs us that, yes, these elliptical galaxies are simply proto-galactic gas clouds which collapsed in a free fall, and then the galaxy was finished in bulk in a very short time, in the free fall time, basically. So the implications of this for the cosmological context, according to the predictions of the standard cosmological model, i.e. the dark matter-based models, done before the James Webb Space Telescope began to observe, the predictions were very robust, and they were very clearly telling us that galaxies should appear at a redshift less than 4, which was then falsified by later JWST observations, and is of course inconsistent with what I just showed for massive elliptical galaxies, which formed at a much higher redshift. And I'll come to the redshift of formation later. As also emphasized here by our recent work in Prague by Zhikang Yan, Teresa Rabkova et al. And Robin Erpen et al. So this figure here is from the paper by Stacy McGough et al., published in 2024, showing the characteristic mass of galaxies at the function of time in the standard model of cosmology, appears the redshift. So these are the predictions made before James Webb Space Telescope observations became available. So they are very, very robust, and these are a clear prediction of these models. So here's the Munich semi-analytical model, here are the illustrative simulations, and these are fired simulations. Very different codes, very different approaches, but the same fundamental lambda CDM theory. So you can see that these independent quantifications of how the galaxy population should evolve in a dark matter-based model indeed tell us that a redshift of 4, before redshift of 4, there was not much to be observed. And they only start emerging at a redshift less than about 4. And it takes time for the galaxies to become massive. So you see here at a redshift of 1 or 0.5, typically the galaxies would achieve the masses we see today for the typical Milky Way class galaxy. It is well known that in the Einsteinian Newtonian gravitation plus dark matter-based cosmological models, galaxies largely grow through mergers. So here's a merger tree from this paper by Stewart et al. And at a high redshift, you can see here 7, the universe consisted of a lot of little dark matter halos, which were maybe forming stars, but barely detectable. It's only with time, you can see here the redshift of 4, that in this case, what later becomes a Milky Way scale mass-sized dark matter halo starts to be noticeable. So this is a redshift of 2.78 here. And as time progresses, smaller dark matter halos with their galaxies merge. So you can see there's a merger tree, like this one here also grows through mergers, but then it merges with this one here. Now, this merging, the fact that these less massive dark matter halos spiral inwards and then merge with the main galaxy, is a consequence of Chandrasekhar dynamic friction. Without Chandrasekhar dynamical friction, i.e. without the dark matter halos around these galaxies, which capture galaxies so that they then spiral inwards, dissipating the orbital energy, giving it to the dark matter halos, structures would simply not form. So the Chandrasekhar dynamical friction is an essential growth mechanism in the lambda CDM model, and we've tested for it in our present-day universe using the small and large magnetic cloud, and it does not occur. So galaxies do not grow like this in the real universe. So this is just a model, and it explains to us why it takes long for the galaxies to actually appear. Okay, you have to wait to a small redshift until we start seeing major galaxies. So this is a merger history of a single Milky Way-sized dark matter halo. And in this model, we have a redshift versus age association, which comes out of the model. So, for example, a redshift of 1, 2, 3, 4 corresponds to an age of something like 1.5 billion years after the Big Bang in this model. Now, a different cosmological model will have a different redshift age association. So, therefore, we measure the redshift, but it does not it does not tell us at which time we are seeing the system at that redshift, because that time is model dependent. This is also important to keep in mind. And here's now an actual simulation, the illustrious TNG 300 case of an overdensity, which will form a galaxy cluster. So we're looking at a region in the universe which is overdense. So already the merging happens more rapidly and structures evolve more rapidly than on the average in the universe. And here's the redshift. You can see the simulation begins at the redshift of 100. And then it jumps very quickly to 9 because nothing happens between 100 and 9. And now we can see these structures evolving. And now we are at a redshift of 6. Not much is visible, a redshift of 5. Now we can start seeing more massive objects. And this is redshift 4, now 3. And now we can really see actually dark matter halos and galaxies emerging. And so this explains how it takes time for these massive systems to grow, and this is already a speeded up region of the universe because of the overdensity. Okay, in less dense regions, this goes much less rapidly. And so this is the inner region of the galaxy cluster, which now has formed these elliptical galaxies. And you can see that the merging continues up until now, continuously. And so we expect the stars in these model elliptical galaxies to have ages which span the entire age of the universe, because what is merging into them are galaxies which are themselves still forming stars. So the Lambda-CDM cosmological model is qualitatively consistent with elliptical galaxies forming from merging disk galaxies. But mergers take time and happen over many billions of years. The implication of this is that elliptical galaxies will typically contain stars with ages spanning many billions of years. And this is shown here in this work in Prague by Robin Erpen et al. So we see here the age spread of the stellar populations in these galaxies. These orange points are central galaxies in the Lambda-CDM simulation, just like we've just seen in the movie. And this is the mass of the galaxy. You can see that the central galaxies are very massive because these central galaxies continue to grow through mergers. And they have, some of them form very rapidly, and then they don't actually form further stars. So these are very old and formed rapidly. However, they are typically, the galaxies have stars in them which have ages averaging about 5 billion years. And this is seen in all other simulations too. So there's a TNG 50 simulation. We have the same, again, the same age spread here, about age 5 billion years. And then we have the Eagle simulations, which are the same model, Lambda-CDM, but with a completely different code, completely different stellar feedback encoded. And again, we see basically the same result, 5 billion years average age for these galaxies. And this is, of course, inconsistent with the downsides. So these curves are what I showed before from the spectroscopic analysis of stellar populations and from chemical evolution models. You can see that the galaxies, the massive galaxies, form on very short time scales, while the model galaxies in the Lambda-CDM model take many billions of years to assemble the stellar populations. So do the observed real elliptical galaxies contain stellar populations with this large spread of ages, as we see in these models? And no, they don't, because we have this downsizing result where the massive galaxies form their stars within 1 billion years and then they stop. So this discrepancy between the theory and what we see in the sky, as shown by these lines here, is a much more than 5 sigma discrepancy, which means, so the Lambda-CDM-produced elliptical galaxies have star formation histories spanning about 10 billion years, so the average age is about 5 billion years in these galaxies, while the real galaxies form catastrophically through a basically free-fall timescale. And this by itself completely rules out these Lambda-CDM models as being relevant for the real universe, because the real universe behaves very differently to what this theory expects. Can dry mergers of ellipticals reconcile the model predictions with downsizing? So in order to save this hierarchical structure formation picture, some scientists thought that perhaps these ellipticals formed from galaxies which themselves were already ancient. And so Pepino and Mattiucci studied this problem and know this suggestion and know very clearly this is impossible. Basically, these building blocks of the galaxies, which then become through mergers these ellipticals, they can never enrich to the high metallicities observed in the present-day ellipticals because they are too low mass and they simply don't have the nuclear processes that can enrich these little galaxies to the high levels observed in these elliptical galaxies. So that clearly is no. Independently, we can look at the following argument. So this is the group of François Hammer in Paris. And they looked at the ensemble of local galaxies, thousands of local galaxies. They find that 3% of the galaxies, so these are all galaxies more massive than about 10 to the 10th solar masses, and only 3% of them are elliptical. So elliptical galaxies are very much the exception. The vast majority of galaxies, 97%, are disk galaxies, so rotationally supported galaxies, where 15% have lost the gas or have not been able to reaccrete gas. The rest are spirals like RMLQA, and then some are peculiar because they look perturbed. So they're probably involved in some encounter with another galaxy, but they're all still fundamentally disk galaxies, just perturbed. And then they redid the same analysis, but for an ensemble of galaxies at a time 6 billion years after the Big Bang. They find that the fraction of elliptical galaxies is 4%, so it's a little bit bigger than today, but they are Poisson uncertainties. And the rest, again, 96%, are rotationally supported star-forming galaxies with S0s still having about the same fraction, as you can see. The spirals, the clear-cut, the clearly well-defined spiral galaxies being fewer, the peculiar class being more, but that's because the universe was smaller, it was younger, and galaxies were simply more interacting. And were still probably forming, and so they were partially unstable, but they are fundamentally, you can see star-forming galaxies which are related to disk galaxies just being perturbed. If they would be forming elliptical galaxies, of course, this would have messed up this fraction here at 3%, right? Because you'd have 50% peculiar, so you'd have a much bigger fraction of ellipticals today. So they settle down to become these galaxies at the more quiet times of our present-day universe. So this is 6 billion years ago, this is present day, and this clearly shows it is not observed, contrary to prediction, that the number of elliptical galaxies increases over time. Instead, in reality, the number fraction of elliptical galaxies remains invariant since the past 6 billion years, half the age of the universe. So elliptical galaxies form early and not over time through mergers, consistent with the above deduction. So you can see that this additional completely independent argument again confirms the previous deductions concerning this statement here. And so we come back to this diagram by McGough et al. We show the mass of the characteristic mass of the galaxy population observed at a given time or redshift. And once the James Webb Space Telescope started to observe, one found that the predictions were completely falsified. One sees massive galaxies at a very high redshift, in fact, much more high redshift than predicted. And it looks like actually the massive galaxies just formed from a monolithic collapse, which is this line explaining the population of massive galaxies at a high redshift. Consistent again with what I was just saying about the monolithic collapse of proto-galactic gas clouds, deduced just from the properties of the nearby elliptical galaxies. And these are high redshift galaxies observed with the JWST, confirming what I said about the elliptical galaxies. You can see a beautiful consistency of the developing theory of how galaxies evolved and formed, which is completely different to what Lambda CDM told us, and very nice consistency with various lines of argument based on empirical data. So thus we have now an impasse or a contradiction. The Lambda CDM model cannot account for the downsizing property of observed galaxies. This is completely impossible in this framework, as long as one sticks to standard physics. And the observed elliptical galaxies instead imply the formation through a monolithic, free-falling gas cloud very early in the universe. So these simulations were done here in Prague by Robin Erpen, where we have the collapse time versus the density of the gas cloud. So we take a mass of a cloud and choose different radii and put that into a computer, allow it to collapse and form a galaxy with star formation, supernova explosion, and so on, just like the movies I've shown. And we do this for different masses so that we span a range of densities here. And you can see that these simulations very nicely show a clear-cut law. So the dense clouds collapse rapidly, and the less dense clouds collapse on a longer time. So this is just free-fall collapse. And in order to actually match the observed downsizing, we identify that actually these galaxies, independent of their mass, must have had radii of about 400 kiloparsecs, so between these two. That then gives us that portion of this curve which agrees with the observed timescales deduced from the stellar populations and chemical elemental abundance analysis of the elliptical galaxies. So this is the free fall time in Newton. What we find is, of course, a different relation. These are Mond simulations, so it doesn't make sense to make these collapse simulations in Newton, because then you'd have to take into account the dark matter and then the hierarchical merging, and that has already been done through the simulations I've just shown, and that is ruled out. So there's no point in looking at the Newtonian case. The Mond-Milgrovian case very beautifully explains actually the downsizing. In order to reproduce the observationally deduced formation timescales, massive elliptical galaxies had to form from protogalactic gas clouds with a radii of about 400 kiloparsec, independently of the mass. So the elliptical galaxies, which the real elliptical galaxies, have supersolar alpha over iron element abundances. So the massive elliptical galaxies had to form within a time shorter than 1 billion times. Basically, they formed most of their stars before supernova 1A were able to contribute iron to the gas. So by that time, the star formation was largely done. They are very metal rich. They have supersolar metallicity. So massive elliptical galaxies had to form with star formation rates larger than 1,000 solar masses per year, with a top-heavy galaxy-wide stellar initial mass function. So we need a lot of massive stars to make these massive, or this amount of metals, and we have the short time scale such that the whole galaxy forms on that short time scale, and so the star formation rate was bigger than 1,000 solar masses per year for the massive elliptical galaxies. And The observationally deduced formation timescales come out from collapsing protogalactic gas clouds from radii of 400 kiloparsec. So we know now that the ellipticals, so the universe seems to have gone through a phase when catastrophically at a similar time everywhere, these ellipticals just fell together from radii of about 400 kiloparsec, and the more massive ones collapsed faster, the less massive ones took a little bit longer to collapse, according to just the free-fall time of the gas cloud. That these results are in contradiction to galaxy formation, the standard lambda CDM cosmological model has been actually known for decades, so this is nothing new. So from the seminal work by Daniel Thomas et al. I'm citing, we show that this finding is incompatible with the predictions from hierarchical galaxy formation models, in which star formation is tightly linked to the assembly history of dark matter halos. Are these high star formation rates actually observed? So we deduce that these star formation rates must have been occurring from the properties of the elliptical galaxies, but are they actually observed? Remembering that around us, the galaxies have much, much smaller star formation rates. For example, our Milky Way, which is a fairly massive star-forming disk galaxy, has a star formation rate of only 3 solar masses per year, and it was not much higher in the past. In fact, if this is constant, we get the baryonic mass of the galaxy quite nicely, which we observe today. So here are ALMA observations of quasar-host galaxies at the redshift of nearly 5 by Nguyen et al. This is about 1.2 billion years after the Big Bang, and you can see here the log of the star formation rate. So this is 1,000 solar masses per year here. This is about 3,000 solar masses per year as a function of the mass of the galaxy they infer. So these are quite massive host galaxies, and you can see that, yes, these such high star formation rates are indeed observed. Implications. We are now approaching the question, how bright were these elliptical galaxies? For this, we need to do a little digression to nuclear synthesis. We know that elliptical galaxies are metal-rich. To build up elements, we need nuclear reactions. So hydrogen combining with hydrogen in the center of a star provides helium and energy, which is why stars shine. So here's the proton-proton cycle, which is active in solar-type stars and less massive stars. We have hydrogen-hydrogen combining to form a deuterium, which combines with hydrogen, a nucleus to form this isotope of helium, which then combines with another isotope, this isotope of helium, which then forms a helium-4 nucleus, releasing 2 hydrogen nuclei. Now, in this network, which builds up helium from hydrogen, you can see that there are these gamma rays which are emitted, and that's the electromagnetic energy which is emitted in this nuclear process, which is why stars shine. This heats the gas in the inner part of the star, sustaining the extremely high temperature. The gravity provides the extreme density of the gas, which at this high density and temperature, i.e. velocities of the nuclei between each other, enforces this reaction, so the helium builds up. If the star has carbon in it, then one can form, the star can have the CNO cycle to form helium, but this works in slightly more massive stars. So we have here carbon, which goes to nitrogen, carbon, nitrogen, oxygen, and again nitrogen, and here it spits out the helium nucleus. Now you can see that this cycle, the CNO cycle, provides again gamma rays at various stages, and this is why these stars shine. So it's an endothermic process. So the nuclear reaction, which builds up from hydrogen, we put in basically hydrogen, we get out helium through the cycle, energy is released. If there is no carbon, then but we have a massive star, then the triple alpha process builds carbon. So we have first the proton-proton chain, which makes the helium. So we have two helium four nuclei, which combine to make a beryllium nuclei, which can interact with a helium-4 nuclei and a nucleus, and then leads to the carbon-12 nucleus. And again, gamma rays are emitted in this process. So once we have carbon, and this actually tells us the energy release as a function of the core temperature in the star. The sun is at this level. Low mass stars sustain the nuclear fusion through mostly only through the pp chain. In the sun, the CNO cycle is active but subdominant. And in the massive stars, which are over here, we get into this triple alpha process, building up carbon, and then also the alpha ladder process, which then goes from carbon over oxygen, neon, magnesium, silicon, and so on, up until iron, each time adding a helium particle or nucleus in the process and releasing a lot of energy in terms of photons, gamma ray photons on the way. So all of that is very well understood. This is nuclear physics. We know this happens in stars, and we know the massives. We need the massive stars to get beyond helium, basically, or carbon. And this diagram tells us the average binding energy per nucleon as a function of the number of nucleons in the nucleus. So you start with hydrogen, climb up to helium, lithium, and so on, carbon, oxygen, and iron. So this rising part is exothermic, which is why stars shine. So the stars create energy, release electromagnetic energy through the buildup in the centers of the nuclei to these heavy nuclei here, iron. But beyond iron, the star then fuses nuclei beyond iron, but that's an exothermic, endothermic process. So it takes energy out of the star. And so this supports the star against collapse because it's releasing energy, so the star cannot collapse. But once this is reached, this peak, beyond that, the fusions continue, but now they take energy away and the star loses thermal support and then collapses. And so we get supernova explosions at this point. But because in this regime, up until iron, it's an exothermic process, and that's why stars shine. Now, stars with masses more massive than 10 solar masses are as bright as 100,000 to a million solar luminosity. There's one star of this mass has this luminosity. So they're incredibly bright. Now, how many massive stars do we need in a massive elliptical galaxy when it was forming to make all these, to make the observed amount of elements? So this is just a question of nuclear physics. It's no exotic physics, nothing strange. For that, we need a little digression into the stellar initial mass function. So we are plotting here the number of stars against the mass of the star. So this is the hydrogen burning mass limit, just below 0.1 solar masses. The sun is about here. Here we have the massive stars. If we count the stars in our galaxy, we find that the mass function they follow, the distribution of the stellar masses, has about this shape. So this is about the salpeter slope here. And the sun, you can see, is already a fairly massive star. It's not a usual star. The usual star in our Milky Way is a 0.3 solar mass star, a little M dwarf. Okay, and so massive stars are very rare in our Milky Way. They are forming, but rarely, very rarely. So that's the galaxy-wide stellar initial mass function. In an elliptical galaxy, to make the galaxy, to enrich the gas so rapidly to supersolar metallicities, we need a huge number of massive stars compared to the low mass stars. So this gives us the luminosity of the elliptical galaxy, which are the stars which are still alive today. And we know that given the supersolar metallicities, we know that we have to put in a huge number of massive stars, many, many more per low mass star than in our galaxy, in order to provide the system with enough nuclear reactions to get to these supersolar metallicities. So as the protogalactic gas cloud begins to collapse, the starburst begins at its center. The central most massive cluster is mostly populated with massive stars. That's where you have extremely high gas density and very low metallicity at the beginning. And this comes from the work of Dabringhausen et al., Michael Marx et al., Teresa Rabkova, who studied in Prague, and Robin Erpen, who did the calculations in Prague, and Eda Georgo, who's working in Nanjing. And we know that when the gas which forms stars in some molecular cloud clump is increasingly dominated by massive stars with increasing density of the clump and decreasing metallicity. So we take a clump, we increase its density, it will make typically more massive stars than what we see in the Milky Way. And if we decrease the metallicity, it makes even more massive stars. Yeah, so that's the idea. And this comes from this work. And so this implies that if we now again have the number of stars per mass interval versus the mass of the stars, but this is the hydrogen-bending mass limit, these are brown dwarfs, and the brown dwarfs follow their own IMF, and that's a separate topic. But the stars follow this canonical IMF with a salpeter slope above about 0.5 solar masses. The sun is about 1 solar mass. Then, so this is typical for the star formation in our Milky Way of the molecular clouds with the metallicity, which is about solar, and the typical densities we see today in the Milky Way molecular cloud clumps. However, if we now increase the clump density, then these clumps start making more massive stars for the number of low mass stars. And with increasing density, this gets worse and worse. If the metallicity goes down, we also get more massive stars. At the same time, taking the metallicity down, we know that this goes down too, because the gas at low metallicity cannot fragment, and so the formation of low mass stars is inhibited. So the modeling of the chemical evolution by Zhikang Yan in Prague with a self-consistently evolving galaxy-wide IMF shows the following. So here we have the time scale. So Zhikang Yan and Teresa Rabkova, who studied also in Prague, looked at a very large ensemble of elliptical galaxies and matched their chemical properties as well as their masses or luminosities, basically. And the findings are portrayed in this diagram. So these are the solutions out of the observed population of galaxies. So we have here the timescale over which the galaxy formed. This is the mass of the galaxies. These are the massive galaxies here, 10 to the 11 solar masses here. And this is the star formation rate in solar masses per year, the fraction of gas converted to stars, and the actual mass of the galaxy, including neutron stars and black holes, which come from the massive stars, divided by the mass in stars, in shining stars. And so we can see the downsizing result again. The massive galaxies must form more rapidly, but this now takes into account the galaxy-wide IMF, as I've just explained, as a function of density and metallicity of the evolving galaxy. So the galaxy self-enriches and the IMF self-consistently changes in these calculations. This is very unique. This type of calculation has never been done until this publication by Zhikang Yan et al. And Teresa Rabkova. So it's actually a major step forward in chemical evolution modeling, with taking into account the self-consistently evolving galaxy-wide IMF. We see that the star formation rates indeed go up to the observed values of about 1,000 solar masses per year, and the gas conversion factor tells us that about a third of the gas mass is converted to stars, the rest is heated up and blown out of the galaxy. And we can see that below 10 to the 10 solar masses, the ratio m dynamical to m star is about canonical, but then for the massive ellipticals, it becomes much bigger. In fact, it turns out that if you look at a massive elliptical galaxy, a large fraction of its mass is actually in neutron stars and black holes. In fact, most of its mass is in neutron stars and black holes. However, these are not concentrated within the galaxy, because as the protogalactic gas cloud collapses and the star formation occurs and the massive stars die, the neutron stars and black holes receive kicks of a few hundred kilometers per second. So as the protogalactic gas cloud collapses, neutron stars and black holes are being ejected out of the system, so that today's elliptical galaxies will have a large mass of neutron stars and black holes in a corona surrounding the galaxy. Some of them will also be in the body of the galaxy, of course, but the galaxy will basically be segregated in the sense that there will be a cloud of black holes and neutron stars, which is as massive and maybe even more massive than the actual stellar mass of the visible galaxy. That's what these calculations predict. So these downsizing results imply that elliptical galaxies formed on a freefall time. These are the times here. And the galaxy-wide IMFs were very top-heavy. They must have been in order to make the galaxies supersolar. So, i.e., basically, these galaxies form from a massive collapsing proto-galactic gas cloud, just like an embedded cluster. And that's quite interesting that the fraction here is about 1/3. It's about the star formation efficiency found for embedded star clusters in our nearby next door molecular cloud clump. Yeah, so these elliptical galaxies basically form just like an embedded cluster. A gas clump just collapsed. In this case, it's a galaxy scale clump, but the physics is fundamentally not different. So how does the stellar population evolve in the forming elliptical galaxy? So this is a grid which comes from the work of Tereza Rabkova, published in 2018, but see also the work of Eda Georgo et al., published recently, which shows basically the same or similar grid. So we can see here, at the time when the protogalactic gas cloud begins to collapse, the star formation is very low, and the metallicity is very low because massive stars haven't yet enriched their gas. So what we see is the number of stars on the y-axis versus the mass on the x-axis. The hydrogen burning mass limit is just here. The sun solar mass is here. And we see the canonical IMF, which is what we get from star counts from the solar neighborhood, has this salpeter slope here, which are these diagonal lines here, and flattens a little bit below 0.5 solar masses. And under these conditions, when the protogalactic gas clouds begins to collapse, the stars which begin to form at the center of the galaxy don't have actually massive stars. So this is the actual distribution of stellar masses at the onset of star formation at these low metallicities. And there's a lack of low mass stars because of this low metallicity. The gas cannot cool and cannot fragment and cannot make low mass stars. And so the IMF at this very early time would have been looking like this red curve here. Then as the time progresses and the protogalactic gas stars begins to collapse more, the star formation rate goes up because the density goes up. The metallicity is still the same because massive stars haven't exploded yet. But what happens because the densities now increase, now massive stars begin to form into dense gas clumps in this protogalactic gas cloud. And it slightly becomes top heavy here, but low mass stars are still not forming because of the very low metallicity. Once these massive stars start to explode, they provide metals, so that as time progresses, the star formation rate increases because the collapse is still occurring, enhancing the formation of massive stars at these very high densities. At the same time, because the metallicity is now increased, the low mass stars start to also form in higher numbers. So you can see that this slope is now flatter because with this higher metallicity, the gas can fragment and start to form low mass stars more efficiently too. And as this peak star formation continues for a short time, the metallicity shoots up because all these massive stars are now dying after a few million years. A massive star at that end, 100 solar masses, dies and explodes. And so now the metallicity shoots up to the supersolar values here, and the gas becomes very efficient in cooling because of this high metallicity to fragment. And now we form a lot of low mass stars, as well as still having a top-heavy IMF. So the IMF, which we see in the Milky Way, which is this concave function, has now turned around. It's now a convex function. It's at the same time bottom-heavy and top-heavy. And this is needed to make the metallicity. And it actually comes out of how we understand how the IMF depends on metallicity. So it's all very beautifully self-consistent. So this IMF is not changed arbitrarily. This IMF is calculated from the physical conditions deduced from observations not related to elliptical galaxies. So it's not a calculation where we adjust the IMF to get this result. No, we do a calculation. Basically, the star formation history is given, which is we get from the collapsing protogalactic gas cloud, and that determines what the IMF must be like in those physical conditions. And that IMF actually turns out to be the IMF we need to get the high metallicity of the galaxy. So it's highly self-consistent now. And then as the star formation declines again, because the gas is heated up, pushed out, and also consumed, the metallicity, of course, stays high. But you can see that the top heaviness starts to decrease because the densities of the star-forming gas clumps have decreased, but we are still forming low mass stars. And as the star formation decreases and becomes to halt, so that we now get the elliptical galaxy as we see it today, after billions of years, the metallicity remains high, and the still forming stars now follow a IMF which is very bottom heavy and lacks massive stars because of the star formation has now declined significantly. And so we have a very good understanding actually of how these elliptical galaxies form in a free fall collapsing protogalactic gas cloud, and the actual processes and radially dependent processes within the galaxy. So the lesson 3 here is that the high rate of nucleosynthesis occurring at high redshift in massive elliptical galaxies implies most of their mass is in neutron stars and black holes, but this can be a halo around the galaxy because of the high kick velocities. And this directly leads to the rapid formation of supermassive black holes in their centers, because the first massive starburst cluster which forms will have a very top-heavy IMF because of high density and low metallicity, producing a very large population of neutron stars and black holes, of something like 1 million neutron stars and black holes within a few parsecs. And as the gas collapses onto it, this is squashed together into the relativistic regime to then catastrophically collapse to a supermassive black hole within 100 million years about. And this was published in this research paper here with Ladislav Schuber, and who's the director of the institute in Prague. So now we come to the final part, which was the outcome of this journey of discovery, which was not anticipated, but it actually comes out of this work on elliptical galaxies and published in this work by Eda Georgo and myself in 2025. Forming elliptical galaxies and the CMB. So we consider an elliptical galaxy, and we now know that the most massive ones formed fastest and earliest. Redshift of about 19. I'll explain in a moment why I think it is 19. They contain about 10 to the 10 solar masses in metals. To produce this amount of metals within less than 1 billion years, they must have been incredibly bright, about 10 to the 15 solar luminosities, bolometric solar luminosities. And they needed a galaxy-wide IMF, which was dominated by massive stars, in order to make these metals, which we see in the galaxies. So here's now the calculation by Eda Georgo, published in our paper here, where we have the growth of luminosity of a collapsing protogalactic gas cloud, which forms a massive elliptical galaxy. So here we have the bolometric luminosity in solar luminosities on the y-axis, and the x-axis is the age. So it starts to collapse at 0, at 1 million years here. This is 10 million years. And this curve here is from a calculation from Zumuzi et al. And this black curve is a completely different calculation in this paper here. And we can see that as the protogalactic gas cloud collapses and the stellar population builds up with this top-heavy galaxy-wide IMF, which we need to provide the nucleosynthesis products, the galaxies become as bright as 10 to the 15 solar luminosities in bolometric luminosity here. And these different calculations, which use very different methods, lead basically to the same results. So these elliptical galaxies were extremely bright. This is the total mass. Of course, the present-day mass is significantly smaller than these masses, because at this total mass, includes the massive stars, which of course die. And so the present day luminous mass of the elliptical galaxies is much smaller, a factor of 10, maybe even 100 smaller than these numbers here. So these are very realistic actual numbers in order to explain the metallicity and the present day masses of the elliptical galaxies. Now, when a starburst is happening, so when the protogalactic gas cloud was collapsing and the starburst was beginning and evolving, a lot of dust was produced. This is seen in every star-forming galaxy, that the galaxy actually, the luminosity of the galaxy is dominated in the infrared. So a galaxy mostly shines in the infrared, which is this peak here. So this shows the flux density, it's a spectral energy distribution from this a chapter in the Encyclopedia of Astrophysics by these people. And so a star-forming galaxy emits mostly in the infrared. The optical part is seen here with the old stars, and then the young stars would be contributing here. The dust takes away this part of the radiation from the massive young stars and transforms this energy into emission at the infrared wave band. So most of the galaxy is brightest in the infrared, in fact, emitting at the dust peak here at 0.1 millimeters. So you can see here, this here is the dust black body re-emission. I'm letting this sink in a little bit. I'm just reading it again. This is the dust black body re-emission at 0.1 millimeter in the rest frame of a star-forming galaxy. Every galaxy has such an SED dominated by emission from a dust black body at 0.1 millimeter. So the protogalactic gas cloud collapse simulations in Prague by Robin Erpen et al. Tell us that the cloud radii from which these collapses happened to form the present-day elliptical galaxies must have been about 400 kiloparsec, for consistency with the downsizing times. The present-day distances between elliptical galaxies are about 15 megaparsec, which means that if the earliest they could have formed so that these gas clouds could have collapsed is at the redshift of 187.5. So we go back in time so that the separation between the present-day elliptical galaxies decreases until we reach a time when they are separated by 800 kiloparsec, when that's the earliest they could have formed. That corresponds to a redshift of 18.75. And magically, if we now think that they are suddenly, so the universe at that redshift started to form all these elliptical galaxies, and they were all emitting mostly at 0.1 millimeter in their rest frame. And we then redshift this to that redshifts as seen today, we end up with a peak emission at 1.9 millimeter seen today, which is exactly where the CMB peak emission lies. And this is crazy, it's amazing. What a coincidence, right? Yes, high redshift galaxies do produce dust, as shown by this paper here by Mitsuhashi et al. So one cannot say that at very high redshift, star formation was magically different without dust. As destiny wanted to have it, in Zoom discussions on the stellar IMF and its variation organized by Zhikang Yang, who did his PhD in Prague, I met a few years ago perhaps the most talented and brilliant young researcher I have ever come to know. Eda Giorgo is very interested in the problems of stellar populations and the IMFs, and is world's leading expert on nuclear astrophysics and chemical evolution. So just the right, brilliant young scientist needed to advance these ideas. So here we can see Eda Giorgo signing a copy of a best-selling outreach physics book she wrote with Margarita Hack. And we got together to investigate the rapid evolution of these elliptical galaxies. So here's now a diagram based on the calculations by Eda of the energy density of the photon field as a function of redshift. That's the photosphere of the hot Big Bang. Assuming it happened, then the energy density of the photons released at that surface of last scattering, the energy density of the photons decreases because the universe is expanding. Then comes this epoch of elliptical galaxy formation at a redshift of about 19, and they provided a photon field which matches that of the CMB. That's just a calculation. It's not tuned to do that at all. This is what comes out taking the separations of the ellipticals today and the arguments I've just brought up. And today we therefore see a CMB from the ellipticals, which peaks at 1.9 millimeter, and this is the real CMB, because these ellipticals exist. Nuclear physics is nothing exotic. We understand it very well. So this is a hardcore result. That's something we cannot take out of the sky. The red curve is the hypothetical emission from the hypothetical photosphere of the hot Big Bang. This is a theory. There's no direct observation of this. This is essentially directly observed. So this is a catastrophe because what we have to do is now we take the observed CMB, subtract the emission of the elliptical galaxies, either this dashed line or this dotted line, depending on the density of the ellipticals. And when we do that, we get to the point that, well, actually, this disappears entirely. So that's, of course, a major implication for all of our understanding of cosmological theory and cosmology in general. And so what we try to do is to see how can we remove this emission of elliptical galaxies. And the best one can do, because the ellipticals are real objects, we can touch them with our telescopes, they're so close, you can nearly walk there, that the best we can do is reduce the emission of ellipticals down to 1% of the red curve, which is at the hot Big Bang emission. But of course, at 1%, and the ellipticals are not uniformly distributed, this completely kills the power spectrum, which is based on fluctuations at the level of 10 to the minus 5. So a 1% contribution on top of that totally destroys what the physical meaning of these fluctuations. So now consider the light emitted by these ellipticals. The average separation between elliptical galaxies today is about 15 megaparsec. The average separation between elliptical galaxies at the redshift of 19 was about 0.8 megaparsec, given this number here. And this is needed in order for the protogalactic gas clouds to have room to collapse. So this means that at this redshift, when the ellipticals were forming, there were 6 massive ellipticals per Planck pixel at this redshift, which means the Planck observations, the Planck telescope was not able to resolve these elliptical galaxies. There was 1 Planck pixel and it had 6 ellipticals on average. So this is about a smooth present-day background emitting at 2.7 Kelvin, just from the ellipticals. So this means then that the Planck CMB is not purely the hot Big Bang. There is a massive contribution by these early forming massive elliptical galaxies. CMB actually might be only the emission from the epoch of elliptical galaxy formation. We don't even need a hot Big Bang anymore to explain the CMB. There is now a highly significant contamination of the CMB by this hitherto unknown foreground. So is there no hot Big Bang at all? And this foreground was not known until now, because as I was showing by that graph from published by Stacy McGough, the lambda CDM theory rigorously predicted galaxies to only start appearing below a redshift of about 4. And so all the corrections done to the CMB observations were done under that assumption. The finding that there are massive galaxies forming at a redshift of 10 and larger, of course, completely upsets the corrections done in the foreground removal in the Planck observations. And so we have this nice cartoon here made by Eda Giorgo, where we have the afterglow of the hot Big Bang. That's the standard current understanding. The universe expands, time proceeds to the right. And the universe, so the photons emitted at the surface of last scattering are redshifted. And then at the redshift of about 19, all these protogalactic gas clouds catastrophically collapse to make the population of elliptical galaxies, which emitted also photons. And today we observe these elliptical galaxies at much larger separations because the universe has expanded. And we see the radiation from these ellipticals, which actually accounts for the observed cosmic microwave background. Plus, there is also a contribution from the afterglow of the hot Big Bang. But the question is now, how big is this contribution, given that we know how many ellipticals there are and we know how much they radiated, so this cannot be removed from the sky. This is just a hypothesis, which can now mean that we can even completely remove this contribution, which now opens the possibility of studying cosmological models where this event happened and what happened before the ellipticals formed becomes a big question mark. Now, this interesting reinforcing evidence, Ericsson et al. And Schwarz et al. Have been pointing out that the CMB has more power and a higher temperature on the southern hemisphere. This is a CMB anomaly, which is somewhat uncomfortable. Now, in a independent publication, Behnam Yavanmardi et al., a PhD student working with me, we published that the southern hemisphere has a much larger number of early type galaxies than the northern hemisphere. In fact, it's much more than 5 sigma difference between the north and south. At this time, I was not aware of these results because I was not thinking about the CMB at all. But and we thought at this time here when we published this that this must be some problem with a morphology classification of galaxies, but we couldn't identify any problem. And this is now discussed in this publication here. Because it now dawns on me that there might be a coincidence, a correlation between these findings. So this is the result from Yavan Mardi and myself. Each point is a galaxy, and the morphological types are given here. So the blue ones are star-forming disk galaxies, and the red ones are the elliptical galaxies. You can see this is the ecliptic here, and you can see that this region has an overabundance of these early type galaxies here. And this is the map of the CMB, the Planck observations, which shows that this part has more power and a higher temperature. And you can see, so this is also the ecliptic, and I look at this correlation from here to there. This looks very, very similar. There's no actual research done yet on whether there is how good this correlation actually is between the nearby elliptical galaxies and the distant emission of the CMB here. Assuming this emission is entirely from elliptical galaxies, it would mean that we are looking at a structure in the universe which spans from our local universe, where we actually resolve and can morphologically classify the galaxies, out to the distance of when elliptical galaxies were catastrophically forming everywhere in free-fall collapse clouds, which is about a redshift of 19. So we are basically seeing from redshift near 0 to a redshift of 19 an overabundance of elliptical galaxies in this region of the sky, which would mean that this whole region of the sky is a significantly over density in the universe spanning across the entire visible universe, which would suggest that we are looking at a universe, at the real universe, being significantly inhomogeneous and being inhomogeneous basically on every scale. And I remind the audience of the existence of the KBC void, which is the local underdensity in which we are located, which also automatically explains the Hubble tension by the dynamics of the void. And so the lesson 4 here is that neither the CMB nor the Planck CMB power spectrum are therefore related to primordial inflation-driven fluctuations. Is all of CMB-related cosmology incorrect? The main evidence for hot Big Bang has therewith vanished. And this is not what I wanted to achieve. It unfortunately now is the result of this research, of this journey of discovery, as we might say. We have to now begin to ask the question that perhaps we can or need to devise cosmological models which are not actually based on a hot Big Bang happening, where at least in cosmological models which do assume the universe is expanding, but which have this one epoch of catastrophic galaxy formation, which we see today as the ellipticals, and which emitted at least a large fraction of the cosmic microwave background. And so the conclusions are as follows. We had lesson 1, that the lambda CDM model is not unique in reproducing the Planck CMB data. Other distinctly non-dark matter-based hot Big Bang models equally fit the CMB data. Lesson 2, which overrides lesson 1, the currently known CMB and its power spectra are only valid for the dark matter-based hot Big Bang models, but these dark matter-based models are falsified by the Chandrasekhar dynamical friction test. Dark matter does not exist, and it will never be found, and it has not been found. You can't find something which doesn't exist. It is wrong to force a non-dark matter-based cosmological model into the published Planck CMB data, and this applies to the Mond community, which is trying to force constructed Mond cosmological models into the Planck CMB power spectrum. That is unphysical. Lesson 3, the high rate of nucleosynthesis occurring at high redshift in massive elliptical galaxies implies most of their mass is in neutron stars and black holes, which are likely in a cloud around them because of the kick velocities which they receive when the neutron stars and black holes emerge from the exploding core collapse supernovae. Lesson 4, neither the CMB nor the Planck CMB power spectrum are related to primordial inflation-driven fluctuations, which means that lesson 4 overrides lesson 2, which overrides lesson 1, but it's consistent with lesson 3. In this view, perhaps all, at least a significant fraction of the cosmic microwave background actually comes from the forming elliptical galaxies at high redshift. More on the details at another opportunity, but it is clear that the current CMB power spectrum has little, if any, physical content. May the one great Knedlik be with you, and therewith I end this lecture with truth prevails. Pravda vítězí is the national motto of the Czech Republic. It is derived from the phrase of the nation hero Jan Hus, who urged people to seek and defend truth.